let's make sure that our oxidation states are correct. So we're going in and we're saying oxygen is 2 minus. We're multiplying it by 3. Gives us 6 minus. And therefore we must have 6 plus. We're dividing by 2. So this is 3 plus. Very good. Again, oxygen is 2 minus. We're multiplying by 3. 6 minus, 6 plus. Because there is only one nitrogen, it is 6 plus. Here this is...
Wait, there's a charge.
There's a negative charge.
Oh, you're correct. So this becomes 5 plus. Just checking to make sure all of you guys are awake. All right. 2 minus times 4 is 8 minus. There is an overall charge of 3 minus. So we must have 5 plus. 5 plus. That is correct. Okay. And last but not least, we have a 2 minus here. This is obviously a 2 plus. Okay. So minimally, let's make sure all of these are correct. Okay. Because if you don't have this correct, I don't know if you can finish with the correct answer at this point. So you're going to draw an arrow to indicate the oxidation and the reduction. And let's look, what is changing? The arsenic is 3 plus. It is becoming 5 plus. So we're going to go arsenic. And we're bringing down the other arsenic compound as well. Okay? And now, I noticed a lot of you made this mistake as I was walking around. Okay? How many arsenics are there here? 2. I must have 2 here. Remember, the whole point is the balance, right? So I must have a 2 here to begin with. Okay? Now, 1 arsenic is 3 plus. This arsenic is 5 plus. So if I had 1 arsenic undergoing this procedure of redox, okay, 3 plus and 5 plus, how many electrons do I need there? I do need 2 electrons here for 1 arsenic. Okay, I need 2. But I have 2 arsenics undergoing this procedure, so it should be 4. Okay, I saw a lot of you didn't have a 4 here. Okay. Then the next one, we're going and we're looking at the NO3 minus. And we're going to the NO neutral. Okay. Here we are at 5 plus. And here we are at 2 plus. So this is quite straightforward. I need 3 electrons on the left side. The 4 and the 3 are not balanced. Okay? So let's make sure they are balanced. So we're going to multiply this equation by 3. So I like to just do this. 3 times 2 is 6. 3 times 4 is 12. Okay? And I need to multiply this equation by 4. So 4 times 3 is 12. 4 and 4. Okay? Everyone with me so far? Okay? Now, the next step is to bring everything down. So I'm going to bring of course my 12 electrons cancel, so I'm not bringing those down, right? But everything else I'm going to bring down. My 3 As2O3s, my NO3 minus, and I have 4 of them. Okay? And I've got my 6 and then my 4 NOs. Now, I like to count. And remember, you got to go water, then H plus, then OH minus. So, how many oxygens do I have here? 9. And how many do I have here? 9 and plus 12 is 21. Okay? I'm counting on you to do the math because I'm terrible at math. All right. How many oxygens on this side? 20. Wait, 6 plus 4 is 24. Sorry, 24. Plus 4 is 28. So the oxygen is 21, 28. So I need 7 H2Os. Very good. Okay? Because I add 7, I should get 28 and 28. Okay. Now my hydrogen count. This is 14. This is none, right? Okay? So I need to add. Now this is where I would stop if I was doing an acidic solution. Okay? But I'm not. I'm doing a basic solution. So I need to add 14 O minuses, OH minuses, to each side. I'm going to add 14 to this side as well. Okay? If that is the case, this becomes what?
Water.
How many waters?
14.
14 waters. And there are 7 waters over there, so they do cancel out, or some of them cancel out. 7 waters cancel out. Okay, so let's bring everything down again for our final answer. We have 14 OH minuses. It should be aqueous. Okay. If you didn't put the states, it's okay for this quiz. On the final exam, obviously, you should put the states. Okay. Did I lose my 3 minus? I lost my 3 minus. I apologize. Okay? And that should be your final answer. Okay? Any questions? There is a shortcut to this, okay? But I won't let you know the shortcut unless you've got this already down, because the shortcut is more complicated, and the shortcut does not allow me to give you partial credit on an exam, okay? Because you're doing it all in one big step, okay? So if you feel confident, then I will show you the shortcut during office hours, but you must first show me that you can do this all the way through without any problem before I show you the shortcut. Okay, because you are at a disadvantage in that you will not get partial credit if you do it that way. Okay? And of course, if you don't want to do the shortcut, you will have plenty of time to do it the correct way on the exam. Okay? Well, they're both correct ways, but the longer way. Okay? All right, any questions? I like to call this shortcut the Dr. Chang way, so it's not the way in the textbook, the way I learned it. Okay? All right. Any questions? All right. Let's pass them in. Okay. Remember, in the syllabus, everybody in the syllabus, okay, 1, not every quiz counts, right? We've taken a lot of quizzes this semester. Okay. How many count towards your final grade? 5. So the top 5 scores count towards your final grade. So you should make sure, go back onto Canvas. I haven't dropped any quiz scores, okay? They're all on there. I will drop them when I calculate the final grade, but right now, all the quiz scores are on there. You need to make sure that you have 5 good quiz scores, okay? There will be another quiz next week on Electrochemistry Part 2, and there will be another quiz on Nuclear Chemistry, okay? So you've got 2 more opportunities at most, if I decide to give both of them. All right. All right, this is Electrochemistry Part 2. Now that we have learned about redox reactions, oh, by the way, this is 151 material, but you do need to be able to identify on the final exam what is an oxidation and what is a reduction. So here you've got your 2 skeleton half reactions. Which one? Raise your hand if you know and can clearly explain which one is the oxidation, which one is the reduction. Uriel.
Is the oxidation the top one because it lost?
Very good. This is the oxidation because it has lost electrons. How do you know that this is the oxidation and has lost? You are correct. How did you figure that out?
Just by looking at the charges, and then pretty much it. Because I saw that 3 plus became 5 plus, so that tells me that it lost. So if it loses,
Very good.
it lost of electrons.
So he's thinking 3 plus became 5 plus. The electrons are on the right side, so this must be an oxidation, right? If this is an oxidation, the other one better be a reduction, which it is. Okay, and it is because your 5 plus is gaining electrons to become 2 plus. On the final exam, there will be multiple choice questions where I give you 4 half reactions, completely unrelated, and you must pick out which one is the oxidation. What is the fastest way to do that? Electrons are on the right side, exactly, right? It's the fastest way. You're just scanning through. You don't have time to read every reaction. You're just looking for electrons on the right side if it's an oxidation. Okay? And again, on a multiple choice exam, if I ask you which one of these is getting oxidized, right? How can you tell? Right. Oxidation, it's on the right side. Reduction, it's on the left side. Very quickly how you can tell, right? Okay? Otherwise, I see students looking at every single equation so diligently, and you're wasting time. A question like that on a multiple choice should take you at most 5 seconds. 1 second for each equation, looking for where the electrons are. You understand? Okay. Just trying to help you be street smart on a multiple choice question. All right. So, you also should be able to identify what is the oxidizing agent and what is the reducing agent. Again, from 151. So again, how do we tell?
Well, the one that's oxidized is the reducing agent.
So the one that is oxidized is the reducing agent. Now be careful. What is being oxidized? Don't write the whole thing. It's not correct. What is being oxidized? The what?
Is that arsenic?
Which arsenic?
The AS.
Which?
On the left side.
On the left side. So this one is being oxidized, right? The correct answer, if I ask you what is being oxidized, you should say your AS3+, right? You must include the oxidation state for it to be a correct answer. If you wrote AS5+, it is wrong because that is the result of the oxidation. The reducing agent has to be what is oxidized. And again, what is the oxidizing agent? Your N5+. So really, your N5+ has to be your oxidizing agent. Okay? Make sure you understand this because these things from 151 will be on the final exam as multiple choice questions. All right. All right. This is kind of like a review of last week's lecture and, of course, last semester. Okay? How do we apply these redox reactions to something we actually care about in real life, practically speaking, right? Always good to know how to do this and to do all the math and electrons, but really, why do we even care, right? We care because redox reactions are the basis for voltaic cells. Okay, I repeat again, redox reactions are the basis for voltaic cells. Okay? Now, how would you construct a voltaic cell? A voltaic cell is another fancy word for battery. Okay? Another word is called a galvanic cell. They all refer to the same thing. So a battery cell, a voltaic cell, a galvanic cell, they all refer to the same thing. Okay? It's an electrochemical cell. It has a system consisting of electrodes that is dipped into an electrolyte. Okay? So in this particular case, you've got 2 electrolytes in their 2 beakers. Okay? And there's a chemical reaction happening on both sides, or what we call your 2 half reactions going on. Okay? And so as a result of this reaction going on, there's a transfer of electrons. Okay? It is a spontaneous reaction, and it generates an electric current as a result of the transfer of electrons. Okay? So an electrolytic cell is an electrochemical cell in which this electrical current drives an otherwise non-spontaneous reaction. Okay? If you can imagine, these markers are electrons. Okay? Right now, in the left-hand beaker, you have zinc 2+ being formed, right? So zinc neutral is becoming zinc 2+. How is this happening? It's losing 2 electrons. So zinc neutral is losing 2 electrons. On the right-hand beaker, you have copper 2+, and it becomes copper neutral. How is that happening? It's gaining 2 electrons. So let's pretend I am the zinc neutral. Okay? Andrew is the copper 2+. So I am constantly, as these two reactions are going, I'm going 2 electrons. And then he becomes copper neutral. I'm zinc 2+, right? Then another zinc comes along, 2 electrons, right? Again, I become zinc 2+, copper neutral. And then another molecule. And this is happening constantly. So constantly there's a flow of electrons from me, from beaker 1 to beaker 2. Do you guys see that? There's a flow of electrons from the left beaker to the right beaker. That's why it has that little electron arrow, and then it's got an arrow going that way. Okay? Now, a constant flow of electrons is just called a current, right? Okay? And this is what drives things like our cell phones, our cars, etc. Okay? So, let's look a little bit closer at that same setup. Okay, again, zinc is on the left, copper is on the right. Okay? Zinc tends to lose electrons more easily than copper. The electron flow from the zinc half cell to the copper half cell results in an electrical current. We call this half of a cell. We call this half of a cell. Because really what is going on here is the oxidation is occurring in this half. The reduction is occurring in that half. Okay? And remember, when something is elemental, that means like zinc neutral or copper neutral, it is a solid or a ion? It's a solid. So it will precipitate. Okay? And if you are zinc 2+ or copper 2+, you're an ion. So you'll be in solution. You will be aqueous. Okay? So let's look. You start off with zinc solid. That's these balls here. It's solid, right? Looks almost like a precipitate, right? And as it loses electrons, it pops out into solution because it is zinc 2+. Does that make sense? So constantly, this is popping out of solution. And as you can imagine, over time, this plate will get thinner and thinner and thinner. The solid plate, as it goes from zinc neutral to zinc 2+ in solution, it's going into solution, so the plate itself will get thinner and thinner and thinner. Now let's walk ourselves over to the other half cell. Now in this particular case, copper 2+ is becoming copper neutral. So really, these 2+ are actually getting deposited or precipitated as a solid onto this plate. So the plate actually gets thicker and thicker and thicker. Does that make sense? Okay? So really, there is a slight problem because what's happening is zinc 2+ is building up in here, right? As the zinc is getting into solution. And copper 2+ is getting put onto the plate. Okay? So you really need to balance out the charge that is building up inside here. Okay? How do we balance out that charge? We have a salt bridge. It's usually just made up of a very inexpensive salt like Na and Cl, Na+ and Cl-. And what happens is the Cl- will come in to pair up with the zinc 2+, right? You have a cation, you have an anion. So there's no buildup of charge. Does that make sense? Okay? So the salt bridge is a tube of electrolyte gel. Okay? Usually you just take, like if you're making jello, you mix gelatin, right? So you have gelatin or agar, and you mix it together with your NaCl. And then as it solidifies inside the tube, you get this gel with NaCl inside. Okay? And it will flow, the ions will flow in the direction as needed to prevent the buildup of charge. Okay? So as more zinc 2 plus ions are produced, the overall charge in the zinc cell becomes 2 positive. That's balanced out by the Cl minus. Okay? And as more Cu2 plus are reduced to Cu neutral, more NO3 minus than Cu2 plus ions are present. So the Cu cell becomes negative, and so it's balanced out by the Na plus. So you always have to have a salt bridge. On the homework, you will have to draw your own setup. Okay? So you should use that picture that we just looked at to help you to draw your own setup. You will be expected to draw and label your own setup. Okay? Now, electrons always flow from the anode to the cathode. Okay? So which one is the anode? It always flows from the anode. The anode is the side that is giving away electrons, right? Okay? So that's where the oxidation is happening. It's the giving away of electrons. Okay? So the anode is always the oxidation. I would write this down as in my notes just to keep track. Okay? The anode is always the oxidation side. And remember, quickly identify oxidation because the electrons are on the right side. Okay? The cathode is where the reduction is happening. And again, a very quick way to identify that is the electrons are on the left side. We feel comfortable? Everyone should write this down in their notes, lecture notes. Okay? So here your zinc is your anode because that is where the oxidation is happening. And again, quickly, the electrons are on the right side. And the copper half cell is where the reduction is happening. And again, quickly we can tell because the electrons are on the left side. You feel comfortable? Okay. Now, if you had to write this every single time, eventually you will get tired. Right? Your hand will get cramped up and you'll be like, oh my gosh, I hate skeleton half reactions, right? Okay? So there's a shortcut way to write this. Okay? We write anode and we get rid of the electrons and we just write the reactant, the product, divided by a line. Okay? You do need to include the states. Okay? The anode is always on the left side here when you're writing it. Then you have a salt bridge. This double line means the salt bridge. Okay? The parallel line, like train tracks. Okay? And then you have your cathode. And again, you have your reactants and your products separated by a single line. Any questions? All righty. So this is the notation for a voltaic cell. On the homework, you will be expected to go from the half reaction skeletons to the notation, and from the notation back to the half skeletons, half reaction skeletons. Okay? So the anode has to be written on the left, the cathode has to be written on the right. A single vertical bar indicates a phase boundary. Okay? In the previous picture, we saw a solid terminus, right? A solid plate of zinc. Okay? And the electrode solution. And of course, the salt bridge is represented by the double parallel lines. Okay? Now, oftentimes an inert material, such as platinum, serves as a terminus and as an electrode surface on which the half reaction occurs. The platinum oftentimes is something that allows the location of the reaction to take place, but doesn't actually participate in giving or taking electrons. Okay? You can think of the platinum or the cathode as something that just is there that allows the reaction to happen. Okay? Now, in the previous example, the zinc is a plate and the copper is a plate. So you have like a solid surface where the reaction is happening already, right? But if you have H plus and H2, is there a solid surface for this reaction to happen? There isn't, right? H2 is a gas. H plus is ions in solution. So you need a surface on which this reaction can happen. And so we have a platinum. Basically, it's just a rod of platinum that you put there that allows you to do this reaction on a solid surface. Okay? Does that make sense? Okay? To indicate that, we just write another line, and then we write platinum. That indicates that it is what is the solid surface, the electrode surface, on which this half reaction is occurring. Okay? Does that make sense? Okay. Now, if it is on the cathode that this half reaction is happening, we put it on the right. If it is on the anode, we put it on the left. But in either case, it's just platinum and then a line, or a line and then platinum. Okay. So let's look at an example and see if we can follow along. Okay. Write the cell reaction for the voltaic cell. So they've given it to you in the voltaic cell notation. Okay? They said tellurium, okay, solid, vertical line, salt bridge, I've literally just copied the A, right? Copied it, okay? So what do they want you to do? What are they asking you to do?
Cell reaction?
Say that again?
To write the cell reaction?
Right, to write the two skeleton half reactions, okay? So this is your what? So let's look. This is your oxidation or reduction? Oxidation. Okay, so let's write the oxidation first. TL solid becomes TL plus aqueous. Okay, it is an oxidation, so the electron should be on the right. Everyone with me? So I've taken this and written it full on, like full half reaction. Okay? Next one, tin, 2 plus, becomes tin, neutral solid. This is your reduction, right? So I need to?
Right, electrons on the one side.
Very good. Is it balanced? No.
No.
Times the top one by 2. Very good. Do we understand how to do this? Okay.
And then we just stop there?
And then you stop there for this question.
Wow, okay, good.
This is a little easier than last week. Wait until we get to why we do this and we use this. Just give yourself a moment in time. Enjoy the simple things in life. All right. Let's do the next one. You have zinc. It is a solid. Vertical line becomes zinc 2 plus. Okay, salt bridge. So notice, they used a comma here instead of a vertical line, right? Do you guys see that? Okay. Why is there a comma instead of a vertical line? What does the vertical line indicate? Well, that's what a comma indicates. But what is a vertical line? What does this line indicate?
That means that's the anode.
Hmm? there's a phase boundary, right? So there's a change of phase. Or like you said, it's a solid to aqueous. Okay, both of the answers are correct. Okay? So you're going from a solid to an aqueous. In this particular case, both of these are aqueous because both of these are ions. So is there really a phase boundary or a phase change? There is not. That's why you need the platinum. Because the platinum is going to be the solid surface where this exchange of electrons is happening. That solid surface is where 3 plus becomes 2 plus. But both of those are in solution. Does that make sense? And you need a solid surface for this exchange to happen, so that is your platinum. The comma indicates that ions are both in solution. There is no phase boundary between the iron and the iron 3 plus and the 2 plus. Because there is no iron solid going on in this case. You understand? Okay. So let's write this out. Okay. Okay. And your other one is going to be iron 3 plus, becoming your iron 2 plus. And you're going to add an electron here. Again, we should balance. Okay. Any questions? Okay. Of course, if I ask for the overall reaction, you need to bring everything down and write the whole reaction. If I ask for the overall reaction. Okay. These kinds of questions with the comma, with the salt bridge, the vertical lines, these are great multiple choice questions on the final exam. I could circle the comma and ask you, what does this comma mean? I could circle the line and say, how come I don't use a comma? Okay? These are great multiple choice questions. There's great extra credit questions where I ask you to explain, why do I use a vertical line? Why do I not use a comma? Right? Okay. Why is there a platinum there? Why do I need it there? Okay. It's because you need it to set up a reaction. Otherwise, what are you going to, you're going to have electrons flowing and then it's going to go straight into a beaker into nowhere? No, that's not possible, right? We need some kind of surface for the reaction to happen. Okay. Now, the next part before we wrap up the voltaic cells chapter, okay, is the idea of cell potential. Remember, the whole idea is you're going to make yourself a little battery, right, where the electrons are flowing from the anode to the cathode. Okay? And you're very much interested in, when you set up this kind of system, what is the cell potential or the electromotive force, the EMF? What is the maximum potential difference between the electrodes of your voltaic cell? Okay? So really, the electrical work is equal to the charge times the potential difference. Remember, work is in joules, charge is in coulombs, and the potential difference is in volts. So those are your key units that you're looking for. Joules, coulombs, and volts. Okay? So the maximum electrical work is in joules. That is equal to the negative of the N. The N is the number of electrons transferred. F is Faraday's constant. You should write this down, 9.6485. So it's something else you should keep note of on your periodic table. The Faraday's constant is equal to 9.6485 times 10 to the 4th coulombs per mole of electrons. Okay? That's something you should keep in case you have a stressful day and you cannot remember your constants. Happens to us all every once in a blue moon. Okay? So let's all make sure to write that down. Okay? Coulombs. I know, my English is bad. You guys have a better way to say it?
I didn't hear what you said.
Coulombs. My dad taught me that. My dad's English is not good. So if your physics teacher taught you something else. Yeah. All right. So I would write this equation, and under that equation, I would write Faraday's constant. Okay? Now, E cell is the cell potential. Okay? So one thing to keep in mind, what is N? Okay? It's the moles of electrons. So let's look here, this equation. How many moles of electrons are being transferred? Being transferred means like I give it to him, the anode to the cathode. Okay? How many are being transferred every time this reaction is happening? 2 electrons, 2 moles of electrons. So in this particular example, N would equal 2 moles of electrons. Let's look at this example that we took on the quiz. How many electrons are being transferred? Let's look. How many?
12.
There are 12. 12 being lost, 12 being gained. So in this particular example, N would actually equal 12 moles of electrons. So if you are going to use this equation, you need to minimally be able to write the half reactions, oxidation and reduction, so that you can figure out what is N. Otherwise, your W or your work will be wrong, right? Okay? Do we understand? All right. Now we're going to look at how you calculate E cell. Okay? But before we do that, let's take a break and talk about a story. Okay? Because we all need a break every once in a while, so I will tell a story. Okay. Faraday's constant, right there, is named after Michael Faraday. He's the nice man with the bow tie there. Okay? He was an English scientist who worked in the field of physics and chemistry. And he's known for inventing the Bunsen burner. Do we all remember the Bunsen burner? Yeah? Okay. He developed a system for assigning oxidation states. So every time you write a circle and assign oxidation states, you should say, "Thank you, Michael Faraday." He's the one who came up with this system, okay, of keeping track of how many electrons are lost, how many electrons are gained. Okay? And he is well known as the father of electromagnetism. Okay? You might think Michael Faraday had rich parents who sent him to Oxford and Cambridge and Superstar, but no, no, no. Michael Faraday came up from a poor family. He stopped going to school at the age of 14.
What?
Yes, as a teenager, okay? Because back then, when you're poor, you have to support and help your family, so you quit going to school to work, right? Okay? But you know what? He found himself a job at a bookstore. And in the bookstore, he was able to read lots of books. And actually, he became friends with the bookstore owner. And back in the day, as part of education, people would hold seminars and lectures. And they were often little cost or free. And so his boss at the bookstore would buy him tickets to go to these lectures. And he would go to these lectures. And he would read books. And he actually kind of was self-educated in that way. Okay? Then, after he worked in a bookstore for a couple of years, he went and became an assistant or a valet. Do you know what a valet is?
Person parks car.
Okay, in this day and age, it's a person who parks cars. But back in the day, he's like an assistant who does things like clean test tubes, do all kinds of things for you. Okay? In a lab, so that he could study chemistry. Okay? Eventually, he never actually attended Oxford as a student, but because of his work in electromagnetism, and his work in oxidation states, they gave him an honorary degree. Oxford did. He is gangster. He is gangster. Okay? So next time you light a Bunsen burner, you write an oxidation number, you say, "Thank you, Michael Faraday." Right? Never ever let your background keep you from doing great things. Right? We all started off with simple, humble roots, right? Okay? If you are persistent, if you study hard, and you're honest with yourself, and you work hard every day, Okay? You too can succeed. It's not about so much about intelligence, it's more about hard work and persistence. It really is. Okay? These kinds of problems seem very difficult at first. I admit it. When I first did it too, I was like losing track of electrons and how many arsenics are moving around, right? But if I do this problem again, do you think I will do better? Yeah. And if I don't get it the second time, I should do it a third time. Don't get frustrated. Don't get discouraged. It just needs more repetition. This is what we call perseverance, right? You just keep going. Try it again. Try it again. Don't get frustrated. Okay? Okay? And don't copy the answer key and say, I did the homework. That's not the point of homework. The homework is to help you and guide you, right? So do it once. Some of you came to office hours today. You got the right answer. Don't say, I just did my homework, I'm done. Now you're going to go back and redo it again. You're going to redo it again. Blank sheet of paper. Redo it again. You got it? Okay. Now, in terms of using this equation, W max is equal to minus N F E cell. Okay? We're looking at the cell potential of a particular voltaic cell. And they gave you Hg2, 2 plus H2, gives you 2 Hg liquid plus 2 H pluses. Okay? And they say that the voltaic cell, okay, has a cell reaction, and it is 0.650 volts. Okay? So let's calculate the maximum electrical work of the cell when 0.5 grams of hydrogen is consumed. So they want you to calculate W max. Okay? But before we calculate W max, let's write down what we know. What do we know? Oops. What do we know? Do we know moles right away just by looking at it? Well, maybe we do. Some of us do. Okay. But what is the best way to figure out moles? Right. So we're going to write your two balanced half reactions. Okay. So Hg, 2 plus H2 gas. Okay? Gives you 2 Hg liquid plus 2 H plus aqueous. So Andrew's suggestion is let's write our two half reactions, and I agree with him. Okay? This is what? Be careful. Be careful. I heard it?
1 plus.
1 plus. Because you're going to multiply by 2 to get 2 plus, which is your overall charge. Very good. Okay. H2. H2 is 0, elemental. Hg is 0, it is elemental. F? No, no, no. 1 plus. There's 2 of them, but each one is 1 plus, right? Okay, when you're doing these, don't look at the stoichiometric coefficients. Okay, when you're doing these, do not look at the stoichiometric coefficients. That'll throw you. Do not look at the stoichiometric coefficients when you're filling in the bubbles. Okay? Then you need to look at the stoichiometric coefficient when you're writing the half reactions. Okay. 1 plus becoming 0. Where do I put the electron? On the left side. This is for 1 Hg. Do you guys agree? But how many Hgs are undergoing this situation? 2. So really you need 2 electrons because 2 Hgs are undergoing this process of reduction. Okay? Now you have H2 becoming sorry, I dropped my states. Okay? Becoming 2H pluses. Okay? And again, I'm going to bring down our oxidation states. Okay? 0 becoming plus. Electron here, right? But remember, that's for one hydrogen. How many hydrogens are undergoing this process? 2. So what is N? So from this situation, we figure out that N is equal to 2 moles of electron. Is this what you were meaning, right? When you were saying write the reactions. Yeah. Okay. Are we good? Okay. What else do we know? Do we know Faraday's constant? Yes. Do we know E cell? What is E cell? Good. So I'm going to do it here. Okay. Under note, my N is equal to 2 moles of electrons. Faraday's constant is equal to
9.6485 times 10 to the 14.
Did we all write this down? Coulombs over moles of electrons. Okay. And our E cell is equal to 0.650 volts. Okay. So we did, we solved for N, right? Now let's plug it in and solve for the W max. Okay? So W max is equal to negative 2 moles of electrons times Faraday's constant times our E cell, 650. Okay, what does this come out to?
One,
1.25 negative, right? 1.25 times 10 to the 5. What are my units? So mole electrons cancel out, right? So really it's coulombs times volts, right? Yes? Yes, yes. It also joules. Okay, one moment. Okay. So this is for how many moles of hydrogen? 2 moles of hydrogen gas? Let's look at the original equation. How many moles of hydrogen gas? 1. The original equation, there is 1 mole of hydrogen gas. So really, this is how much work is the result of 1 hydrogen molecule undergoing this process with, of course, mercury and all of other stuff, right? Okay. But they say you have in your reaction flask how much? 0.500 grams. So this is really per 1 mole of H2. Does this look like a conversion factor? It does indeed. Okay, so what is my given? Very good. My given, so now I'm going to solve for the second, or the last part, which is for 0.500 grams. Okay? So my given is going to be 0.500 grams of hydrogen. And I'm going to convert to what? From grams to moles of hydrogen. And then from moles to Coulomb volts. Okay? This is simple enough to do. This is just a conversion factor problem. How do I go from grams to moles? Hopefully you all know this. Periodic table. What should I write here? 2.016 if we want it to be very exact. Right? And here it's 1 to negative 1.25 times 10 to the fifth. This is just our conversion factor from up above. Okay? So this comes out to
negative 3.13 times 10 to the 4th.
So my grams cancel out, my moles cancel out, I am left with Coulomb volts. Remember what I said back in 130 and 151, conversion factors will haunt you all the way through the end of chemistry. Okay? They never leave. They never leave. Okay? Any questions? No questions? All right. Feel comfortable using this equation? Okay. So, we often have something called a standard cell potential and electron potentials. Okay. And so we're just going to look at some generalized half reactions. Okay. We like the zinc and the copper because they both give you 2 electrons being exchanged or transferred. Okay. So oftentimes we like to look at the zinc 2+ and the copper 2+ because perfectly balanced in its exchange of 2 electrons. Okay? So we say that the reduced species becomes the oxidized species plus n number of mole electrons. That is the oxidation at the anode. And you have the oxidized species. You're gaining n amount of mole electrons, and it produces the reduced species. And that is happening at the reduction side where their cathode is. Okay? So really, what does E cell mean? I mean, we used it. We said it's 0.6 or 0.5650 volts. What does that really mean? Okay? That is really the result of 2 things happening. Okay? It is the result of a push and a pull. Okay? Let's say that there's a block sitting right here. Okay, there's a block. Okay? And on one end of the block, I'm here, and I am pushing this block, trying to get it to move. Okay? And I am not strong enough and apparently pregnant, so I cannot get this thing to move. Okay? So what can I do to help move it along? I can recruit somebody else to help me, right? I can get Shimona to come up and say, hey, get on the other end of the block and start pulling, right? So then if I'm pushing and she's pulling, we might be able to get it to move, right? And if we get it to move, it is the result of my pushing energy plus her pulling energy. Does that make sense? Okay? So in an electrochemical cell, okay, the work is going to be the result of, on one hand, in one cell, the electrons happily moving and being given away. And on the other hand, the other cell is like, give me, pull, give me the electrons. Right? On one hand, it's the push, giving away electrons. On the other hand, it is the pull, or the pulling in of electrons. Does that make sense? Okay? So really, we say the zinc is your push, your copper is the pull. The zinc is the giving away of electrons. The copper is the gaining of the electrons. Does that make sense? So we say the E cell is equal to the E of the copper and the negative E of the zinc. Another way to write this is E of the copper minus E of the zinc. You've just rearranged it mathematically, right? Okay. So remember, the copper is the anode or the cathode? It is the cathode. This is the anode. So really, E cell, let's distill it down and add to our situation here. E cell, can't spell cell, is equal to E of the cathode minus E of the anode. Okay? Or the E of the reduction minus E of the oxidation. Okay? Any of these will work. Okay? Are we good so far? Okay. So, you can actually look up the numbers for standards. And this is actually in the back of your homework booklet. Okay? These tables are in the back of your homework booklet. Okay? It is also in the back of the textbook under the appendix. Okay? Where you were looking up delta H, delta G, delta S, same place. Okay? And so you can actually find the anode, find the cathode, and subtract the two numbers and come up with an E cell. That's where they came up with the E cell in the previous problem. Okay? So really, the standard cell potential, E, and the standard is again represented by the little degree symbol in the top right-hand corner, is the electromotive force, or the EMF, of a voltaic cell operating under standard conditions. And for you to have standard conditions, you must have a solute concentration of 1 molar. You must have a gas pressure of 1 atm. And the temperature is usually 25 degrees. The values in the textbook are calibrated to a standard hydrogen electrode. Other electrodes include carbon and gold. Okay? Just keep in mind that the standard is hydrogen, but if you use carbon or gold, you need to look up charts for the carbon or gold. They have charts for each one. Okay? When I was in grad school, I was using a carbon electrode, and I was looking on a hydrogen chart, and my numbers did not make any sense. I was redoing the basic thing to test it and saying, how come it's not right? And then I realized I was looking at the wrong chart because I was using a carbon electrode. Yes, do you have a question?
Yeah, is this electronegativity? How much?
No, so the electronegativity has to do with if you have a bond and I can pull the electrons more, right? So this is sort of similar to that, but in a electronegativity kind of thing, we're looking at a covalent bond, right? But in these cases, these are all ionic situations. Zinc becoming zinc 2+. Okay, so this is not quite the same thing. Okay? You're just comparing how much the zinc wants to give away 2 electrons and how much the copper wants to gain 2 electrons. Okay? So really, you've got your E cell is equal to the cathode minus the anode. Okay? And your book walks you through this complicated way of doing it where you take your 2 half reactions, you do this, and then you subtract the 2 like in Hess's law. Okay? And you can do it that way and get the same exact answer. I think it's easier just to do cathode minus anode. You will get the same answer whether you apply Hess's law and do 2 elementary reactions, get the overall reaction, and then add your E cells, or if you just do cathode minus anode. Okay? Okay? Really, the first way is just Hess's law redone again. Okay? But the second way, you have to remember flip it because on this table, this is all, notice, all the electrons are on which side? Huh? All the electrons are on the left side. So this is all what? Reductions. So if you're going to pull from this table and write an oxidation, you're going to need to flip the sign, right? Because you need to flip the reaction, right? So that is why the anode is always negative. Because if you pull it off of the table, it's going to be a reduction and you want an oxidation for the anode. Does that make sense? Okay? So let's look at one. Let's do one together just for kicks. Okay? You've got your aluminum going to aluminum 3+. So let's find that on the table. And if you can't see this, you should pull out your homework booklet and find that particular reaction. Homework booklet, you should be looking at the table that's given to you for half reactions. This is your aluminum, solid, becoming your aluminum 3+. So let's just do a quick review before we go too far ahead. This is our standard cell notation, right? Is this the anode or the cathode? It is the anode. What about this side? This is the cathode. Okay? So we're looking at the table and we're finding aluminum and aluminum 3+ an exchange of 3 electrons. Where is that? Do I see it somewhere? The 1, 2, 3, the fourth one down, right? Right? Negative 1.66. Did we get that? Okay. So this is negative 1.66. You guys agree? All right. What about the iron? 2+ to the iron solid.
Negative 0.04.
Yeah, 0.41. Is that what you got?
Oh, they're different ones for different charges?
Yes.
Okay.
Negative 0.41. Right? We're pulling the numbers straight from the table. That's all we're doing. Okay. Literally straight from the table onto your piece of paper. Okay? So, now we're going to apply our equation. E cell is equal to what? What subtract what? Cathode is this one, right? So negative 0.41 subtract our anode. Don't lose your negative sign straight from the table, otherwise it's wrong. Okay? So this is really what? This is really plus, so it is 1.25 volts. If you pull it straight from the table, you don't need to change any signs. You just need to plug in, because the negative sign takes care of that. Okay? Negative sign will take care of the flipping and when you do Hess's law. Okay? Any questions? No questions. All right. Let's do another one quickly. Okay? You've got your zinc, solid, becoming zinc 2+. And you've got your copper 2+, becoming copper neutral. Okay? Again, this is your anode, and this is your cathode. So let's pull from our table again. Let's find our zinc, 0.76 negative. Are we there? Am I right? Am I wrong?
You're right.
Okay. And then the copper, do I have a positive 0.34? Am I close? Okay. So again, our E cell is going to be what? 0.34 minus a minus 0.76. Or plus 0.76. And this comes out to positive 1.10 volts. We good? All right, let's take a break here. Come back in 5 minutes. Charge it. The excess, so your car is, I'm not a mechanic, so this is just like a very generalized way of thinking about it. But basically, when you run your battery, and you ride your car, your battery is actually not what is running your car. It just starts it. Then what is running your car is the gasoline that you're burning in a regular, not a hybrid car, you can have a regular car.
Yeah.
So then there's extra juice as you're moving your car forward. And that extra juice is taken, and the alternator takes that extra juice and converts it and stores it in your battery to recharge your battery so your battery never runs out or until it gets really old. It's like I eat a ton of donuts.
Yeah.
Okay, I'm burning fuel, like I'm burning gasoline, right? Like donuts are gasoline, right? So that allows me to do all this kind of work, right? Teach and run and frisbee. But there are some extra calories that don't get used up because I don't play enough frisbee and I don't walk around enough. So where does that get put? That's fat in my hips, right? Do you agree? Okay, and my belly and my butt, right? Okay? So the alternator takes the extra juice that you have when you burn gasoline and you're driving your car, right? And you're moving your car forward, takes that extra juice and stores it back into the battery. And of course, there's only a certain amount that the battery can hold, but it can't hold all this, but enough to just every time you want to start your car, you can start it. And you want to run the radio or headlights or whatever, there's enough juice in there. Does that make sense? Now, I haven't really studied hybrid cars and how that works, so I don't know exactly how that works. I haven't done any studies on it. Right back. For those of you who are coming back, you should all do exercise 19.9 and solve for minimally delta G, using that equation, okay? So you should use this, solve for E cell, right? Plug that in, you have Faraday's constant, figure out what is N, and solve for delta G. Everyone do it now. I want to see 2 half reactions. Everyone do it now. I'll be right back. Last time. Good? All right. So, ultimately, we can also calculate delta G using a very, very similar equation. So we're going to add to our little table of equations, okay? And we have delta G is equal to minus N, Faraday's constant, E cell. Okay? So how would we use this equation? Let's look. You have a regular standard redox reaction. You identify what is your cathode, what is your anode. And once you have identified what is your cathode and anode, you can either use Hess's law like they did there, or you could do E cell equals E cathode minus E anode. Either way, you're going to figure out E cell. Based upon your two half reactions, there are 2 electrons being exchanged or transferred. So N is equal to 2 moles of electron. And you have Faraday's constant, which hasn't changed since we last talked about it. And you can find delta G. So they did an example for you here. Okay? 2 moles of electron, Faraday's constant. You've got your E cell. You get negative 3.01 times 10 to the 5th. Notice the unit. What is the unit there? Joules. So really, your moles of electron cancel out. So you're left with coulombs times volts, right? So remember, coulombs times volts is the same as joules. Joules, same thing. Okay? So you see joules, you should think coulomb volts. You see coulomb volts, you should see joules. Okay? Let's look at exercise 19.10. Let's do it together. Again, we are solving for delta G. Okay? I would say the first thing you should do is identify what is your anode, what is your cathode. So you're going from tin, 2 plus, to tin what? 4 plus. You guys see how I pull that out? Okay? And since it's aqueous to aqueous, I should not use the line, I should use the comma. Okay? It doesn't say what electrode I'm using, so I'm just not going to put it for now. Okay? And then I'm going from to, is it Hg2 plus? To Hg2 2 plus. Okay? So how do I find E cell? How do I find N? Of course, Faraday's constant is 9.6485 times 10 to the 4th coulombs over moles of electrons. Okay? How do I find E cell? Who can help me?
Well, we have to probably write the half reactions to make it easier on ourselves.
Okay, let's write the half reactions. Sn. Well, do you really need the half reactions to do E cell? You can. Okay, but really, the left side is always the anode. And the right side is always the cathode. So I think I would do what Andrew was doing and look it up right away from the table. Okay? Tin 2 plus to tin 4 plus. Finding it is half the battle, I agree. Right there. Do you see it? Midway through. 0.15. Okay? We're going mercury aqueous to mercury aqueous 2 plus, but this is Hg2 2 plus. So again, we're looking for mercury, and I see it here, right? 0.90. Am I close?
Yes.
Yeah, 0.90. Oh, yes. Did I write? I wrote. I wrote the wrong one. This is 2 plus to 2 plus. Which one? Yes, it is the same thing. 2 plus to 4 plus, 4 plus to 2 plus. Remember I said, okay, this is all reductions. Do you remember? Okay? And this is an oxidation. You're just trying to find the oxidation, but the oxidation obviously will be flipped. Does that make sense? Or do I need to go over Hess's law again? I can do that. No? Okay. Is everyone with me, or is anyone confused? It's okay if you are. Mercedes, are you with me?
Yes.
Okay. So we're going to do what subtract what to get E cell? Cathode minus anode. Seven, 5 volts. Okay. What is N? Now, in this case, if it helps, the half reactions would maybe a little bit. Okay. So we're going from tin, 2 plus, to tin, 4 plus. We need 2 electrons on this side. We're going from mercury, 2 plus, to mercury, 2 plus. Let's think about this for a second. This mercury is 2 plus, right? This mercury is what?
Plus.
Plus, or 1 plus. Very good. Okay. So for 1 mercury, we have 1 electron here, right? For 1 mercury. But we have 2 mercuries, so really we should have 2 electrons. Do we get that? Are we, everyone with me? So really, what is N? 2 moles of electron. Okay, I think we have everything we need to solve. This is our no. Let's solve. Okay, to solve, we're just writing our equation. Delta G is equal to minus NF E cell. So really it is minus 2 moles of electron multiplied by Faraday's constant, 9.6485 times 10 to the 4th coulombs over moles of electron. And we're multiplying by E cell, which in this case is 0.75 volts. 5 moles of electron do cancel out. And I end up with
Negative 1.4 times 10 to the 5th coulomb volt.
Or we can write negative 1.4 times 10 to the 5th joules. Not per mole. Moles have canceled out. Oh, I see what you're saying. It is joules per mole of, for example, tin, or joules per mole of mercury, but not mole electrons. Okay? So you're right. It is joules per mole of whatever is in the original reaction. Okay? But the moles of electron have canceled out. Okay? Any questions? So do you think if I calculated for the top reaction using numbers from my delta G table, I will get a different answer or a same answer?
Same.
I will get a same answer. If I took this, I wrote the overall reaction, which would basically be this, okay? And I took and found the G values, the Gibbs free energy values for this, 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 and this, and I did sum of the products minus sum of the reactants, I will get the exact same answer, or very, very, very close to the same answer. Okay? These two values are the same. They're just two different ways of solving the same thing. Is everyone with me? Okay? So really, let's do another example just to make sure we are all on the same page. Okay? Suppose the reaction of zinc metal and chlorine gas is utilized in a voltaic cell in which zinc ions and chloride ions are formed. So you're basically going zinc solid reacting with chlorine gas. That forms zinc 2 plus and 2 chlorine ions. Okay? So they say calculate the standard potential for this cell at 25 degrees from the standard free energies of formation. So in this problem, are they asking you to calculate delta G? Initially, but ultimately, what are they asking you to calculate? ultimately at the very end?
Standard potential.
Standard potential or E cell. They want you to calculate E cell. Okay? And they ask you to use, from your appendix, the table of Gibbs free energy values. So I've pulled them for you. Okay? Zinc is 0, chlorine is 0, zinc 2 plus is minus 147, and chlorine minus is minus 131.3, and there are 2 chlorines. Okay? So if we were on the last exam, okay, how would we solve for delta G? The sum of the products, very good, minus the sum of the reactants. Okay? So really it is what subtract what? Minus 147 plus 2 times negative 131.3. We're going to subtract our reactants, which is all 0, right? Okay. This comes out to what?
And that negative 409.6, but someone's saying for a second that.
And from our table, the Gibbs free energy is in kilojoules per mole. Okay? Did everyone get negative 409? Andrew? No. What did you get, Shimona? We're going to take the majority and go with this number. It's okay, Andrew. No worries. All right. So, you have delta G. You have Faraday's constant. Do you have N? Sure. Okay, let's look at it. Zinc, neutral, becoming zinc 2 plus. I need 2 electrons on this side, right? Okay, then I go from chlorine, neutral, to chlorine minus. Okay, again, very easy. Chlorine is 0, chlorine is negative. So for 1 chlorine, you need 1 electron here, right? But how many chlorines are undergoing this process? 2, so you need 2 electrons. Okay, so really, what is N? 2. Okay, and if you rearrange that original equation, the delta G is equal to N minus NF E cell. You're solving for E cell, so E cell is really equal to delta G divided by negative NF. Do you guys agree? I'm just rearranging it algebraically. I have delta G. Okay. I have N. And I have F. But Faraday's constant is in joules. Right? So I can't use kilojoules. I need to convert it to joules. Do you guys recognize this? Okay? So really I need to go kilojoules, 10 to the third joules. Right? Because my original equation is in joules. For me to do any kind of math, I need to be in the same units. Okay? Any questions about this situation? Okay? this comes out to, oh, I lost my 10 to the 4. So don't forget the power of 10s. Just do this divided by this, right? What do we get? 4, oh, huh? 2.12, like that? Oh, you solved the whole thing. Okay. And what unit should I be in? Volts. Very good. Do you need me to walk you through the units? We're good? Okay. If you need me to walk you through the units, come to office hours. I'll walk you through the units. Okay? Some of you might be magically thinking, how did she get volts? There's no volts here. Okay, come see me in office hours. All right. Or you can just do some algebra. All right. Now, knowing E cell allows the calculation also of the equilibrium constant, K. And this K is either Kc, Ksp, Ka, or Kb, depending on what kind of reaction you have, right? So we're just going to put K, but in the back of your mind, you're thinking this is very much tied into all the previous chapters on equilibrium constant Kc, Kb, Ka, Ksp, so on and so forth, right? Kf, Kd, so many. Okay? So, looking at example 19.11, okay, they say that the standard cell potential for the following voltaic cell is 1.10 volts. That is the E cell. And they ask you to calculate the equilibrium constant, in this case Kc, for the following reaction. Okay? Now, just as a very, very quick overview of how they get to this equation that we're going to use, okay? We know from this chapter that delta G is equal to minus NF E cell. Okay? We also know delta G from our previous chapter is equal to minus RT ln of K. So if we set those two equations equal to one another, okay, minus NF E cell must equal minus RT ln of K. We're setting those equal to one another because they both equal delta G. Okay? So if I'm solving for E cell is equal to minus RT ln of K over minus NF. Do you agree? Divided both sides by NF. Okay? The negative signs do cancel out. It is really equal to, and I'm going to pull out everything that is a constant. And my equal signs are gone. My negative signs are gone. So I'm going to have RTF okay, and then I have 1 over n, because n is on the bottom, and then ln of K. Is everyone with me? Okay? So if I got rid of the ln and replaced it with log and folded that into this constant here, I'm going to get, and they calculated it out for us, 0.0592, okay, divided by n, okay, log of K. Okay? So they basically taken these two equations and distilled it down into an easier equation where instead of having to plug in 3 different constants, You just use this number here. Okay? If you wanted to do that, you'll get the same answer. You will. I guarantee it. Okay? So you should write this down in your periodic table. Okay? Should add it to the growing list of equations that we have. So looking at this equation and pulling out what we know, okay, we know that E cell is equal to 1.10 volts. We know that N is equal to 2 moles of electron. This is our basic zinc and copper. We've seen this like 10,000 times today. Okay, what is K? So we're just going to solve. Very, very simple. E cell is 1.10 volts, is equal to 0.0592 divided by 2 moles of an electron times log of K. Okay, how do I solve this? Nobody knows. Wait, what? Not yet. I need to multiply by the reciprocal to get rid of this thing first. I can't raise to the power of 10 first. Right? First. What does she want us to do? So yes, we're going to multiply by the reciprocal to get rid of this. So we're going to go 2 moles of an electron divided by 0.0592 times 1.10 volts. I think that's what she was saying. Equals log of K. Then we raise the whole thing to a power of 10. This cancels out our log, so K is equal to this whole thing. Okay? I think that's what she was trying to say. Shimoda's like 10 steps ahead of me. She's like, next problem. Did you solve this yet, Shimoda? Let's solve this real quick. I'm risk averse, so I do this first, hit answer, then equal, then 10 to the answer. But Shimoda probably did it all at once. I'm so proud of you. What did you get? 37. Can someone confirm this? You got? Okay, good. Very good. All right. So this is KC. As a very quick review, if this is our KC, is it mostly products or mostly reactants? Mostly products, because it's a huge number, right? Okay, which is good, because if it's a negative number, then this battery is no good, because it's mostly reactants, okay? For this to work, your battery needs to be mostly products as you're running this reaction, right? So, I like this table, or this graphic, figure, whatever you call it, because it puts together everything we've learned from all our previous chapters. Okay? We initially started out by looking at equilibrium and saying that equilibrium can be expressed as a ratio of products to reactants, which we're going to call K. Do you remember back then how easy life was? It was just products over reactants, right? Then we folded in the idea of delta G, and we said delta G can be calculated by saying minus RT ln of K. So if you have the equilibrium constant, you can calculate delta G, the Gibbs free energy, to tell you if something is spontaneous or not spontaneous. And then we said wait a second, if you can calculate delta S and delta H, entropy and enthalpy, you can also solve for delta G and get the same answer and predict spontaneity. Now we're going to fold in one more thing where you can calculate the E cell and get delta G, or get delta G and calculate the E cell, or you have E cell and you can calculate K like we did over there. Or if you have K, guess what? You can calculate E cell. Okay? This is kind of like overall what we've learned so far. Okay? Any questions? So, one more final thing. So far we've done this, and this is all at standard conditions, right? So who remembers what were some of our standard conditions? 1 ATM, 1 molar, 25 degrees or 298 Kelvin, right? Okay. And one of the things that is really important is the 1 molar. 1 molar says that's the concentration. Okay? So we've been doing all of these calculations assuming, for example, our zinc concentration is at 1 molar. Our copper concentration is at 1 molar in our little beaker. Okay? But in all reality, oftentimes the concentration is not 1 molar. Do we agree? Okay? So there is a dependence on concentration. Okay? And this was discovered by German chemist Walther Nernst. He derived an equation for the cell potential for various concentrations in gas pressures. Remember, gases, the pressure was 1 atm for it to be standard, right? So the Nernst equation says that E cell, and now notice, this E cell has no little circle, right? The little degree sign. That means it is not at standard conditions, okay? But it is equal to the standard conditions minus 0.592 divided by n log of Q. Remember, Q means that it is not at equilibrium. Very good. Okay? So this allows us to look at the concentration, the electrochemical potential of a cell at an instantaneous time given the reaction, where Q is very much like you calculate QC, products over reactants, right? Just like Kc, but not at equilibrium. Okay? So you're running a reaction, it is now at equilibrium, and you say cadmium becomes cadmium 2 plus, and the cadmium 2 plus at that instantaneous time is 0.0100 molar. Then on the other half reaction, you have H plus at 1 molar, and it is becoming H2 at 1 atm. Okay? So really Q is equal to products. So they rewrote it all out in all its glory. Okay? Products, which is CD2 plus concentration. Now notice, this is a gas. So when we have a gas, easier to measure the partial pressure, right? Do you guys remember? So we're going to stick in the partial pressure, not the concentration, divided by our reactant, H2, and we have to square it because the stoichiometric coefficient is 2. Okay? Why did we not include this in our Q?
Solid.
Because it is a solid and its concentration does not change. Very good. Very, very good. Okay? These are all great final exam multiple choice questions. Okay? So as we're asking ourselves these questions and walking through, we should be checking off, do I know the answers to these, right? Okay? You will have 50 multiple choice questions on the final exam, and you should be able to speed through those at about, I would say, 15, 20 minutes. Less than a minute a question. Okay? So therefore, to calculate Q, it is just the concentration, partial pressure, divided by the concentration squared, which is here. Okay? And then you can plug Q into your Nernst equation to solve for E cell. Okay? Any questions? All right. So we're looking at it. Okay, new problem. Okay. So you've got your E cell. Your E cell is 1.10 volts. You've got your zinc concentration and your copper concentration from your problem. Again, notice the concentration is written in your cell notation in parentheses. Right next to zinc 2 plus, you have parentheses 1 times 10 to the minus 5. And next to copper 2 plus, you have in parentheses 0.100 molar to indicate the two concentrations. N is equal to 2. Again, during the homework, if you're unsure what N is, what should you do? If you're unsure of what N is as you're doing the homework, don't just write 2. What should you do? You should write the skeleton half reactions. Okay? In this case, I can quickly eyeball it. Zinc is going to zinc 2 plus, copper 2 plus is going to copper neutral. I can quickly eyeball that, right? So I don't need to write it out. Okay? But if you did need to, I wrote it out here just to double check. Okay? And therefore, you're going to solve for Q first. So Q is equal to products minus reactants. So Q is equal to the zinc concentration, which is 1 times 10 to the minus 5. And the copper concentration is 0. I'm just going to write it in scientific notation. 1 times 10 to the minus 1. Do we agree? There are no stoichiometric coefficients, so nothing needs to be squared or cubed or anything like that. Okay? The zinc solid and the copper solid does drop out of the equation altogether because it is solid and the concentration doesn't change. Therefore, Q is equal to 1 times 10 to the negative 4. No molar, sorry. Q has no units, right? Okay. To solve for E cell, I will need E cell standard minus 0.0592 divided by N. N is 2 moles of electron. And I need to multiply by log of Q. Okay, how am I going to solve for E cell? It's given to you in the problem. Okay? But if it wasn't given to you in the problem, how would I solve for it? I heard it. You need to do the cathode minus the anode. Okay? So on the homework, some of the problems will not give you E cell as the number. You need to calculate it first. Okay? This comes out to 1.10 volts minus, what is this whole thing? Did anyone calculate it yet? Log of 1 times 10 to the 4th is just is equal to 4, right? Okay. From pH chapters? No? No? Okay. What is this first? Tell me this first. The sooner we get out of here, the sooner we can go down to the 90 minutes around the world and get free food.
You said right there?
Uh-huh.
The first spot?
Uh-huh.
Shimona, back me up.
What?
I have a number I just don't know if it's right.
Yeah, I got negative 0.1184.
Negative
That's what I got.
Shinoda,
0.1184 like this?
Yeah.
Yeah.
Okay. Shimona, can we confirm? Okay.
And the final answer is 0.9816.
0.9816.
816. Unless you want to put it scientifically.
No, we'll just
How's
leave it.
that? You said don't you add those?
I think it would be 1.2.
Yeah.
Oh yeah, you would have it.
1.2. 2,
1,
1, 8, 4. Let's just call it 2, 2. Round it to 3 sig figs. Do you understand how to do this? Okay. We have to get used to reading the standard cell notations. That's the shortcut notation, okay? Last but not least, okay, one more example. You've got your zinc solid becoming zinc 2 plus, and again, you've got your nickel and your nickel solid. Now, in this particular case, they are not asking you to solve for E cell. What are they asking you to solve for? What is the nickel concentration? Notice, next to the nickel 2 plus aqueous, there's no concentration written there, right? So how would you go about doing this? I'm going to walk you through it. You know your E cell, okay? How do you solve for your E cell standard? Cathode minus anode. So we're going to do that, cathode minus anode here, and we get 0.53. I've just looked up those two numbers for you, okay? With this, you should be able to solve for Q. Okay, so we've plugged in our E cell at non-standard conditions. We've plugged in our E cell at standard conditions. Minus 0.59 divided by 2. It is 2 moles of electron being transferred. Log of Q. If you work the math all the way through, Q is equal to 2.623 times 10 to the 6. Okay? Q will allow me to solve for the nickel concentration because Q is equal to zinc divided by nickel concentrations. So to solve for the nickel concentration, just algebra, that is equal to 3.81 times 10 to the minus 7 molar. Okay? This is just math. We're just working the equation backwards. Okay? Any questions? No questions. All right. Last but not least, we do have the stoichiometry of electrolysis, where 1 Faraday is equal to 9.6485 times 10 to the 4th coulombs per mole. Does that look like a conversion factor? The units of coulombs divided by moles of electrons. Sure, it's a derived unit. Okay. Where you have 9.6485 times 10 to the 4th coulombs is equal to 1 mole, the thing in the bright yellow box. Okay? Additionally, coulombs, this nice new unit that we met today, is equal to amperes times seconds. This will allow us to calculate the amount of charge from the amount of product in an electrolysis. So you've got your aqueous solution of copper sulfate. It's going from copper 2 plus to copper solid. Okay. The other electrode reaction is H2O becoming O2 with the transfer of 4 electrons. So if a constant current was passed for 5 hours and 4.04 milligrams of mercury metal was deposited, what is the current? Okay. To solve for the current's unit is in amperes. Okay. I say amperes. I think some teachers say amperes, like P. I like it makes it sound like AF. Okay. Up to you. Up to you. Shimoda, what did your physics teacher say? Amperes. Amperes. I like the way I say it better. All right. It is a unit for current. Okay. So, and again, you might be like, oh, Dr. Chang, this is too much physics. Actually, this is just chemistry because it is just a conversion factor problem. Really. 404 milligrams of copper was deposited. Can we convert to grams? Sure. Can we convert from grams to moles? Sure. Can we convert from moles to moles of electron? Sure. Right? 1 mole of copper will give you 2 moles of electron, right? Very good. Can we convert from moles of electron to coulombs using Faraday's constant? Sure. Okay, so let's just set it up really quick because we love conversion factors. We surely do. 404 milligrams milligrams to grams of copper, grams to moles of copper, moles to moles of electron, and moles of electron to coulombs. Okay? So really, 1 10 to the third, 1 copper is 63.5. 1 mole of copper gives us 2 exchanges of 2 moles of electron transferred. 1 mole of electron per 9.64585 times 10 to the 4th. Okay? This gets us what? For those of you who are using calculator, 10 to the third, 10 to the fourth leaves 10 to the 1, right? Okay, 404 times 2 times this divided by this is, what do we get? We'll ask Shimona and then we'll get someone to confirm. Go, Shimona. Okay, and what unit should we be in?
Huh?
What units are we in?
Joules.
Coulombs, right? Everything else cancels out. We're in coulombs, right? Okay, and coulombs is equal to what? Is really equal to amperes times seconds. Oops. Right? So this is for how long? How long are we doing this reaction for? 5 hours. So 5 hours, no. 5 hours is really how many seconds? A lot. 5 times 6 is 30. 30 times 6 is Are we close? Let's assume it's right. Okay? So if this is how many seconds, you're going to have to multiply it by the ampere seconds to get 5 hours. I'm not going to do that math. We all know how to multiply. Okay. This is ampere seconds, right?
Yes.
Right? But we have this many seconds. You've got to multiply these two numbers together. Okay? All right. Any questions? So, in terms of next week, let's make sure to finish the rest of chapter 19, the homework booklet, all the way through. Okay? We will start chapter 20 on nuclear reaction next week. We should be able to finish nuclear reactions next week in one lecture. Okay? Then on December 4th, we will review for the lecture. Okay? And then on December 11th, we will have the final exam. Any questions? No questions. Okay? There will be a quiz on part 2 of electrochemistry next week. So for those of you who are checking on Canvas and saying, I don't have 5 good quiz scores, you need to really take it seriously. And some of you, listen, some of you have not submitted your Canvas quizzes. I bet none of them, or maybe only one of them. I won't mention any names this week, but next week I will start mentioning names. And the shame will begin publicly. If you don't want to be publicly shamed next week, like in Game of Thrones, I'm just kidding. I won't make you walk naked down the aisle. But if you don't, I will find you and we will have a conversation and I will say, son, why, son, have you not done any of the Canvas quizzes? Listen, each Canvas quiz is worth 20 points. 5 Canvas quizzes is how many points?
20.
Shimona? Each Canvas quiz is worth 20 points. 5 Canvas quizzes is worth 100. Is that the same as one exam?
Yeah.
Yes. If you don't turn those in and submit those, that is like saying, I'm just going to get a 0 on an exam. Why? That will bring you up an entire half a letter grade. If you're sitting at an 85, you can be at a 90. If you're sitting at a 90, you could be at a 95. I'm just saying. All right? So, please do your homework, do your Canvas quizzes. If you are struggling with the Canvas quizzes, you should come see me. We can do it together, and then you can hit submit, and everything will be perfect. Okay? All right. I have office hours today until 1 normally, but there is 90 days around the world, so I'm going to go get some free food first. Then I'll meet you up in my office. I believe it is.
Last time they had a lot of donuts.
Really?